Hey, welcome back to Math with Patrick and Quill. Today is December 1st, and we're solving problem 335 from the Daily Epsilon calendar. And the answer today should be 1 because that matches today's date. So we have a limit problem, and then once we find the limit, we're going to take the natural log of it, and hopefully we get 1 to match today's date. And if we do take the natural log of something and get 1, that something just needs to be the number e for this to be true. So I'm going to kind of ignore that natural log on the outside a little bit, and I just want to show that this limit, as n goes to infinity, of the nth root of n to the power of n over n factorial, I want to show that this number is just e. And I think one way we could do it is actually to use Stirling's approximation. This is, I don't really know how he found it, but it's a way to get a nice asymptotic similar expression for the factorial function here. And it's going to be, so this little squiggly says asymptotically similar or the same. Basically, once we are in limit land going towards infinity, these two things are essentially the same value. It's going to be the square root of 2 pi n times n over e to the power of n. There we go. And let's see if this is helpful at all. So limit as n approaches infinity. I'm going to distribute this nth root to the top and bottom. So we have the nth root of n to the power of n, and then the nth root of Stirling's approximation here. So we're going to get 2 pi n, and then times n over e to the n. Seems like I'm complicating it because I have square roots in nth roots now, although I do think they are going to cancel. On the top, they definitely do. The nth root and the power of n just cancel out their opposite operations, so we just get n on top. And then I am going to distribute this nth root to both. Dealing with the second one first is a little bit easier. That power of n and that nth root cancel again, so we just get n over e. And then we do get something a little bit weird here. We get the square root of 2 pi n to the power of 1 over n. That's the same thing as an nth root. I'm just changing it to a fractional exponent. Also, I could change this square root to, say, a power of 1/2. And then also I could multiply my fractions there in my exponents. And then finally, I have some expression here. And this goes there. And basically, I want to show that this is the number 1. So let's attack this kind of weird expression together here. Let's just see what happens if we try to do direct substitution on this limit. We could try plugging in infinity for the n here, and then infinity for this exponent up here. 2 times infinity is infinity. And essentially what we're getting is infinity to the power of 0. And this is a little bit strange. Not sure how to deal with that. Instead, let's use a logarithm to get this exponent down somewhere a bit more manageable. So I am going to take the natural log right here. That does let me take this 1 over 2n out front as a factor instead. And real quick, let's see what this is actually doing to my limit, right? I wanted to show that this was the number 1. And so if I take the natural log of 1, I would get 0. Now limits and algebra steps are quite friendly. So the natural log of a limit is the same thing as the limit of a natural log, like that. And so because I want to show that this is the number 1, if I take the natural log of it, I want to show that this will give us a 0. So I took the natural log. It's still going to be a limit as n goes to infinity. Here we can write it as a fraction, natural log of 2 pi n over 2n. And at this point, I can see that the linear term is going to grow much, much faster than the natural log term in the numerator. So this tells me it's 0. We could also use L'Hopital's rule here to demonstrate that same idea. Why not? The derivative of the top is going to be 1 over 2 pi n, but then chain rule says multiply by 2 pi, so these actually cancel out. And then the derivative of the bottom is just 2. And then if we plug in an infinity here, we do get 1 over infinity. That's 0. 0 divided by 2 is 0. So backtracking, We did get 0 from this limit. That means this one without that natural log should be 1, which means I can actually evaluate this 1 right now and just do that a little bit soon, I suppose. And then we have n over e. This simplifies to just e, just some fraction arithmetic there. And with Stirling's approximation, we're done. We did show that this limit is equal to e. Plugging it in here, taking the natural log, we do get 1. So this is one way to solve it. Technically, we're done as long as you are fine using Stirling's approximation. However, there's a second way to solve it, and we don't need to rely on this approximation to get the answer today. For the second solution, let's again just kind of attack this middle part here and ignore that natural log on the outside. Let's distribute that nth root so we still just have the n in the numerator, and then we have n factorial. And again, I'm going to express the nth root as a fractional exponent instead. Here, I think a logarithm is going to be helpful again. That's because we have kind of like a variable in the exponent place, and logarithms are helpful in removing very valuable variables in exponents where they're a little bit harder to access. So here I am taking the natural log of the limit again. So this one's supposed to be e. So now that I've taken the natural log of it, I'm expecting it to be 1. So let's just kind of keep some notes here. I want to show that this is going to be the number 1, and that's equivalent to solving the problem for today. Let's use another log rule here. I'm going to split the log of a quotient into the difference of logs. And then I'm going to use another log rule right here where the log of something with an exponent here, that exponent can come out as a factor in front. And this is still the limit as n approaches infinity. Currently, if we try plugging in infinities, we would still get infinity minus 1 over infinity times infinity. And this is still a whole jumbled mess, kind of hard to see what's going on. So we need to do more. And I am going to take a look at this expression right here, the natural log of n factorial. This is, for example, let's just say n is 6, just to kind of see what's going on. This would be the same thing as natural log of 6 times 5 times 4 times 3 times 2 times 1. And when we have the log of a product, we're allowed to write it as the sum of logs. And so we could split all of these up with addition. I could write this in summation notation like this. Let's use maybe k as our variable to increment, k from 1 to 6, natural log of k. And so this sum and that sum are the same thing. They're just written in different notation. However, we aren't using 6 today. We're using n. So I could replace this 6 with n, like that. So all of this is actually just useless now. It was just kind of there for example, just to show that I could think of this chunk as an infinite sum. Infinite because n is going towards infinity. And I want to bound this infinite sum on both sides just to kind of get a good sense of what its value is as it approaches infinity. Of course, it's going to kind of explode out of bounds because we have terms that increase, and then also we have an infinite number of terms. So this sum diverges, but I kind of want to know how it grows. I'm going to use integrals, I think, here to bound it from above and below. And the idea being, let's draw a natural log graph real quick. The idea being that we can kind of think of it as like a Riemann sum, it being our sum here. And then we can find some integrals that kind of overestimate and then underestimate our Riemann sum. Taking a look at this graphically, the sum includes all of these points right here. And we could think of it as a Riemann sum where we have rectangles whose widths are 1. And so we can kind of convert the idea of adding up a bunch of values to adding up area of rectangles. The sum goes from 1 to n. And so here it looks like we're basically doing a left Riemann sum from 1 to n plus 1. Although this Riemann sum, the rectangles, is undershooting the actual value under the curve from 1 to n plus 1. So what we can do here is do an integral from 1 to n plus 1 of natural log of x dx. And this integral is going to overshoot this value, and we can visually see it with all of this kind of extra area between the rectangles and the curve. Now, just for the sake of the problem today, I think instead I'm going to do 1 to n. And so conveniently, I'm forgetting this last rectangle here. But then I will just add on this extra value right here. And so I'm taking the integral from 1 to n. I still have all of this kind of headroom right here, which means that this value is going to be, the integral value is greater than the rectangles. But then if I add on ln, there we go. So that includes this value, and then the integral kind of overshoots the rest of the sum. Let me write this a little bit better. There we go, plus, and then ln n. On the lower side of things, I could just take that integral from 1 to n, natural log of x dx. There we go. That's the integral from 1 to n, and then it kind of undershoots the overall sum. Again, the whole sum we can think of as all of these rectangles. If you imagine shifting over all of these rectangles one spot, then they are going to overshoot the curve, and therefore this Riemann sum is greater than the integral. Just for kicks, let's actually do the whole integration by parts to do the integral of natural log of x. We can say that u and dv are equal to, let's say, ln x and then dx. Du is equal to 1 over x dx. dv, or v, is just equal to x. And then the integral of u dv should be equal to u v minus the integral of v du. Doing the substitution, u times v is x times natural log of x. V du is going to be these two multiplied to each other. The 1 over x and the x cancel out to just get a 1. So the integral of 1 dx will just give us x. And then we do have a plus c if it were an indefinite integral, but since we do have bounds, we can wait for later and plug in the 1 and the n. So it's going to be the same thing over here. Let's just kind of get those inequalities here, pretend that I rewrote this there. And it's the same integral on the right side, so we'll have x times ln x minus x evaluated from 1 to n, and then plus that natural log of n at the end. Again, that just kind of makes sure that the right integral does actually provide an upper bound on our sum, our Riemann sum in the middle. Let's evaluate top and bottom. So we get n times natural log of n minus n, and then minus 1 times natural log of 1, but natural log of 1 is 0, so that doesn't do anything. But we do get the minus x, so it does pop a minus 1 on the end there. Let's do the same thing over here. It's going to be the same expression, n times ln n minus 1, then just plus this 1 more natural log of n. And so our sum, I'll just put an s here for sum, is bounded between these two values. Let's look up what we're doing from the problem at hand today. Remember this 1 over n that I kind of captured in my little net? I got it from the exponent spot, and I'm able to use it a little bit more readily. This 1 over n is multiplied to ln of n factorial. And so I could multiply the 1 over n here and here because it is part of the problem. And then let's distribute this n. So to the first term, the 1 over n and the n go away, natural log of n. To the next term, 1 over n, or times n, is 1, so it's minus 1. And then we get minus 1 over n. We'll just kind of think about that middle term, the actual sum, in a sec. And then on the right side, we get the exact same thing, ln n minus 1 over n. It's just that we have this extra little term here, plus ln n over n, and then now we have a bound for our sum. Let's go back up to the problem again and think, okay, we were actually taking a limit as n goes to infinity, so let's see if we can have any simplifications due to the fact that n is approaching infinity. ln n is still going to be the same, minus 1 is still the same, but in limit world, 1 over infinity is just 0, so I can conveniently forget that part. We'll just kind of keep this 1 over n times that sum there. On the right side, that ln n and minus 1 are the same. This 1 over n goes away for the same reason. And then earlier in the video, I did show that if we do have the limit as n approaches infinity of a natural log term divided by a linear term, this also goes to 0. And so in our limit, we get the upper bound and the lower bound are the same. Therefore, the middle number has to be the same thing. I can, in my limit, replace this kind of sum expression, or the factorial one, with just natural log of n minus 1. So let me write that in a different color just so I can squeeze it in here. I can replace this whole chunk with natural log of n minus 1. And then now, when we evaluate our limit, maybe let's distribute that negative sign to make it abundantly clear what's happening. Those two natural logs go away, and we just get a 1. And that actually is our answer today, right? Because maybe you saw my little editor's note that this natural log here could be placed on the inside. And then now that I've proven that this limit is 1, that shows that the inner limit is e, and then once we take the natural log, we get 1. So that's the problem. There's 2 different ways to solve it. As far as I know, maybe there's more, but I figured I'd show both just to show you different ways of trying to solve this problem. So we're all done for today. Thank you for watching, and I'll see you tomorrow. Bye.